Hello friends. So today we are going to solve two questions which were asked in the year 1997. So in the first one, an infinitesimally small bar magnet of dipole moment m is pointing and moving with a speed v in the positive x direction. A small closed circular conducting loop of radius a and negligible self-inductance lies in the yz plane with its center at x equals 0 and its axis coinciding with the x-axis. Find the force opposing the motion of the magnet if the resistance of the loop is r. Assume that the distance x of the magnet from the center of the loop is much greater than a. So in this case, we can draw an approximate diagram. Suppose this is our x-axis. We have a small magnet which is moving along x-axis with the velocity v, and we have a circular loop which is conducting and whose center is at x equals 0, and the center also coincide with x-axis. Okay, so this is a rough approximate diagram of the given question, and we have to find out the force opposing the motion of the magnet if the resistance of loop is given as r. So in this case, we are going to start with the magnetic field of the dipole at the loop. And the distance of this magnet from this center is given as x. So we are going to start with the magnetic field of the dipole at the loop. Magnetic field of the dipole at the loop, and that can be written as b of x is equal to mu naught upon 4 pi to m and divided by x cube. And we have to keep in mind it is given that x is very much larger than a. Now, based on this magnetic field, we can find out the magnetic flux through the loop. Magnetic flux through the loop. And phi will be equal to b a, and magnetic field we already know is our mu naught. We can write this as 4 pi, and here we have 2m divided by x cube, and the area will be pi a square. So here pi goes with pi and 2 goes with this 2. So therefore it can be written as mu naught m a square divided by 2 x cube. And based on this magnetic flux, there will be induced EMF in the loop. So we can find out the induced EMF in the loop, and which can be written as induced EMF E is equal to minus d phi upon dt. and we substitute the value, we get d of dt is equal to mu naught upon 2, and here we have ma square upon x cube. So we are going to derivate this our x cube, and this gives us that the induced EMF will be equal to mu naught m a square upon 2, and this comes d of dt and x raised to power minus 3. And now this can be written as mu naught m a square upon 2, this comes as minus 3 x raised to power minus 4 dx upon dt. And it is given in the question that the magnet is moving with the speed v. Magnet, or rather we can say speed of the magnet, speed of magnet is given as v, and which can be written as dx upon dt. Therefore, the EMF induced E can be written as, this comes as 3 by 2 mu naught m a square and x raised to power 4 and multiply by v. So we were able to find out the induced EMF in the loop, and because of this EMF there will be current flowing in the loop, or we can say induced current in the loop. We can write induced current in the loop, and the loop is having a resistance R. Induced current in the loop having resistance is equal to R. Therefore, we can say our I will be equal to induced EMF divided by R, which gives us 3 mu naught m a square v divided by 2r x raised to power 4. Now we can find out the dipole moment of the induced current. We can say magnetic dipole moment, of the induced current, and this can be represented as small m, which will be equal to I multiplied by A. Current we just calculated, we can substitute the value, we get this as 3 mu naught m a square v divided by 2r x raised to power 4, area will be over pi a square. So we get our magnetic dipole moment m will be equal to 3 pi mu naught m a raised to power 4 times v divided by, this comes as 2r x raised to power 4. Now we have two dipoles. One is the magnet, original magnet, which is having a dipole moment of capital M, and then there is an induced dipole. So both will be interacting with each other, and there will be resultant of a force. Okay. So we can say that force between two dipoles, So we have original magnet which is having a dipole moment given as capital M. Then we have induced dipole, which is in case of the loop, we have induced dipole, and which is having a dipole moment of small m, So therefore there will be a force F between these two dipoles. So we can say the force F between these two dipoles, and we can write that force F is equal to 3 mu naught upon 2 pi m dot small m divided by x raised to power 4. And we substitute value of small m in this particular equation. This will be coming as 3 mu naught upon 2 pi x4 multiplied by capital M, and substituting value of small m, which was our 3 pi mu naught capital M A4 V, and this is divided by 2r x raised to power 4. 2r x raised to power 4. So we can just simplify by multiplying it. We get force F will be equal to 9 mu naught square, and we have this is m square a raised to power 4 times v divided by 4r x raised to power 8. Okay, so this is the force. Now we can find out the direction of the force. Direction of force. Now the direction of the force will be our according to the Lenz's law. So we can say by Lenz's law, the induced current creates a magnetic field that opposes the change in flux. Induced current creates a magnetic field that opposes the change in flux. So as the magnet is moving towards the loop, so therefore the induced dipole will oppose this motion. So we are given that the magnet is moving towards the loop. So we can say the induced dipole will oppose this motion. The induced dipole will oppose this motion, thereby creating a force opposing the magnetic moment. Thus, the force will be in the negative x direction. So we can say the induced dipole will oppose this motion by creating a force that opposes the magnet's moment. So from here we can say that the force is in negative x direction. The force is in negative x direction, or we can also say opposing the velocity, opposing v. Therefore the opposing force, because in the question it is asked about the opposing force, therefore the force opposing the motion of the magnet is equal to F, and we are going to have a negative sign, and this will be our, we just found out the value of F is our 9 mu naught square m square. 9 mu naught square m square a 4 v divided by 4 r x raised to power 8. Or if we are only interested in magnitude, we are just going to ignore this negative sign. So this completes the first question. In the second question, which is also asked in the year 1997, it is said that a pair of parallel horizontal conducting rails of negligible resistance shorted at one end is fixed on the table. The distance between the rails is L. A conducting massless rod of resistance R can slide on the rails frictionlessly. The rod is tied to the massless string which passes over a pulley fixed to the edge of the table. A mass M tied to the other end of the string hangs vertically. A constant magnetic field B exists perpendicular to the table. If the system is released from rest, calculate, we have to find out two things here. First one is calculate the terminal velocity of the rod, and the second is the acceleration of the mass at the instant when the velocity of the rod is half that of terminal velocity. So we are given this diagram. So we have a rod and which is attached to a mass M using this pulley, and the magnetic field which is perpendicular to the you can say table, and the direction is given in upward direction. In the first part, now we are going to find out the terminal velocity. So we start with part A. So we know as this rod is going to move in the downward direction, or we can say toward the right on the table, and because of this there will be an induced current, and all these things will be you can say induced current will be because of the change in the flux and something like that. So we are going to start with the induced EMF, because the velocity v is given, that it is moving with the velocity v. So let us say it is moving with the velocity v. So you can say when the rod moves with the velocity v, with the velocity v, the induced EMF will be equal to BLV, and because of this there will be induced current. So therefore we can say the induced current, or we can say the current I will be equal to induced EMF divided by resistance, which is R. So this comes as BLV divided by R. So because of this there will be a magnetic force acting on the rod, and it will be acting in the opposite direction according to the Lenz's law. So you can see from here the magnetic force let us call that FB, acting on the rod opposes the motion. And that is according to Lenz's law. So we can write FP will be equal to ILB, and we already know value of I. We substitute it here, we get this as B square and L square V divided by R. And we are supposed to find out the terminal velocity. So it means in the downward direction it will be moving with the velocity V, and that will be because of this weight, and that downward force will be given as mg, and there will be force on this rod which will be acting to a direction opposite to a direction of motion, which we called as fp. So for terminal velocity this mg will be equal to fp. Therefore we can write at terminal velocity we can say we can represent this v as now vt. Therefore our mg will be equal to fp. We substitute the value. Fp is our b square L square Vt divided by R will be equal to mg. Now it's a simple calculation. We get our terminal velocity Vt will be equal to mg R divided by b square L square. This is our terminal velocity. So we found out our first part. Now in the second part it is asked that acceleration of the mass at the instant when the velocity of the rod is half that of terminal velocity. So we have to find out in part B. Part B, acceleration when velocity is half of the terminal velocity. Therefore we substitute value of Vt, we get that our velocity will be equal to mgr divided by 2 b square and L square. And the magnetic force, in this case we also try to modify it. So now we can write that our magnetic force, because now rod will be moving with the velocity v, so magnetic force, our Fb will be now our b square L square v upon R. We substitute the value of v in this equation, we get this as b square L square upon R multiplied by mgr divided by 2 b square and L square. And here this b square, r and r cancels out. We get our magnetic force Fb will be now equal to mg divided by 2. Now it is said that acceleration of the mass. So it is this mass will be now having an acceleration in the downward direction. Let us suppose that acceleration is given as a. And if it is accelerated motion, obviously there will be net force acting on the mass. So we can just redraw an approximate figure of that. So this is the rod and it is connected with a pulley and we have mass mg. In this direction we are going to have mg. A rod will be having a force in the opposite direction, that will be our Fb, and it is said that it is going to have accelerated motion a in the downward direction. Therefore we can write, because of this accelerated motion a, we can say that the net force acting on the system is a rod as well as the mass. Net force acting on the system, and system is mass m plus rod. Okay, so this is mass m and this is our rod. So we can write the equation that F net will be equal to mg minus Fb. We substitute the value of Fb, so we get this as mg minus, and this comes as mg divided by 2, which comes as mg divided by 2. Now this is the accelerated motion, therefore we can say that the acceleration a, and it is also given that the rod is massless. Okay, so we can say that total mass of the system, is m, as rod is massless. Therefore acceleration a will be equal to net force and divided by m, and net force we found out is mg divided by 2. So we substitute it is mg divided by 2 multiplied by 1 upon m, and here m and m cancels out. So we get that the acceleration a is equal to g upon 2. So when the velocity is half of the terminal velocity, the acceleration of the system or of the mass is g by 2. So you can say this is the acceleration of mass m, or we can also call it a system, because the rod is massless, so indirectly it comes as a, we can say for system also, when velocity is equal to half of the terminal velocity. So this completes the second question. So these two questions were asked in the year 1997. So this completes the questions. Thank you.